Good afternoon, good evening, or good morning, whenever it is you're watching. Thank you for tuning in to Ms. Hernandez. Today we're going to be covering in our chemistry class section 5.3, Quantization of Energy. And remember, this is the same thing that's in your packet from CK12. Okay, it is the same presentation, except it's in a PowerPoint for mostly for my students who are with me live to make sure that they are listening and they are understanding the content. So we have been talking these last couple of days about the electromagnetic spectrum, and today we're going to be talking about different forms of electromagnetic radiation and how they release energy. Okay, release or absorb energy. Okay, so who's going to help me with the introduction today? Fifth period.
Every so often you hear a commercial or a new story with the words quantum leap in it. The quantum leap is supposed to be a major breakthrough, a big change, something extraordinary. ¿Qué dice ahí, miss?
Extraordinary.
Large. The reality is far different. Instead of the big extravagant change, the quantum that scientists know about is a very small difference in the location of an electron around a nucleus, hardly an enormous shift at all.
Thank you, Alexia. So, when I was a young student, young teacher, I was learning about these quantum leaps, and every time I heard quantum leaps, I was thinking of the TV show from the 90s where a man, was doing quantum leaps, and his quantum leaps was basically him traveling throughout different times. Uh, throughout time, right? He would go back to the Western civilization. He would go into the early 30s, different, basically any time period in the past or any time period that's in the future. And that was that was a quantum leap to me. It was basically a big jump in time. But as I started to study more and more chemistry, I learned that a quantum leap is just an electron jumping to a different orbital or a higher orbital. So in the case of hydrogen, you have one electron in energy level number 1. So if energy comes and hits that atom, the electron is the one that's going to get affected. And what happens to the electron is it goes from being in orbital number 1 to being in orbital number 2, or maybe orbital number 3. It just depends on the amount of energy that is hitting the atom hydrogen, or the hydrogen atom, right? If it's a low frequency energy, it might just jump one orbital. But in the case of its high frequency energy, then it could jump, more than one orbital. But that is what it is. A quantum leap is a change of energy levels for electrons, right? It's originally in energy level number 1. It could jump into energy level number 2, or it could even jump into energy level number 3 if the energy that's hitting it is strong enough. Okay, and here you have a picture, and maybe I should have made this little one a little bit bigger, but you have two examples of two different types of quantum leaps. In this case, you have a long frequency, a long wavelength that's hitting that electron, and it's only jumping one energy level. But in the case of a short wavelength with high frequency, you have it jumping two energy levels. Okay, so it can jump, or it can leap more than one energy level depending on how much energy is being absorbed from that electromagnetic radiation. Um, it also describes a quantum of energy being the amount of energy needed to move an electron from the original present energy level to the next higher level. The term quantum leap comes from describing the sudden change from one level to the next. And we're talking about these levels being these orbitals where electrons rotate. The higher the energy level, the farther you get from that nucleus. Always remember that. As you're jumping into a higher energy level, you know you're moving further and further away from your atom's nucleus. Quantization of energy. Now, the German physicist Max Planck, who was around in the mid to late 1800s, early 1900s, studied the emission of light by hot objects, right? So it emitted, anytime you heat up an object, it emits a certain electromagnetic radiation, a different form of light, okay? Um, and you have probably likely seen this picture that you see below if you've been in a welding class, or maybe if you've even seen um, uh, videos where a welder is working. Even in the movies you'll see welders, and as they're working you'll see that the metal starts to kind of have a glow to it, and most of the time it looks like an orange kind of red color. And so Planck, what he did is he studied that light that we were seeing, this light that we're seeing in the picture with these three gentlemen. And the caption for this picture says that a heated object may glow different colors, right? And depending on the color, well, it'll have a certain frequency, right? It'll also have a certain wavelength. And you can measure that, and you could analyze that, and you can calculate how much energy that object is radiating, it's releasing. The atoms in this piece of metal are releasing energy in discrete units called quanta, and that is applicable to all objects. Okay, if you can get heated and you glow a specific color, you're releasing energy in units called quanta. Okay, and think of it as little bursts of energy that's being released. Okay. And here you have your first question for those of you who are in the pair deck. When metals are heated, they glow an orange red in color and release energy in units called quanta. Is that a true statement or a false statement? If you're not in pair deck, you should be entering in the Google Meet chat. If you're not in pair deck, and I know some of you guys are not, make sure you're entering in the chat on Google Meet. Is this true or is this false? What do you think, guys? And those of you who are in pair deck, Yalexia, Irvin, is that a true statement or is that a false statement? What do you think, guys? 4 people are in pair deck and only 1 person has answered. Can I get some more answers, please? Make sure you're listening, please. Make sure you're listening because it is asking you a question. True or false, anytime metals are heated, they glow orange and red in color and can release energy in units called quanta. 2 people have said that is correct. And you know what? Those 2 people are correct. Yes. Anytime, and we can go back and we can talk about it, and you can see here, anytime a metal object glows, in this case, an orange-red color, it is releasing energy in units called quanta. So that is a true statement. Very, very good. Now, let's talk about classical physics. This is, before the time of Max Planck. Classical physics, which when you're studying classical physics, you're explaining the behavior of large everyday objects. They predicted that a hot object would emit electromagnetic energy in continuous fashion. Basically, energy is always being released constantly without interruption. Okay, without interruption. That's what they thought at the beginning. In other words, every wavelength of light could possibly be emitted. Okay? Every form of light could possibly be emitted. Now, instead, when Planck was doing his studies, he started analyzing the spectra of this light, right? He specifically was analyzing, what was being emitted. And by analyzing that spectra, he found that the energy of the hot object could only be lost in small, discrete units. Okay, so you basically, it's kind of like mini bursts of energy, mini bursts of energy. Think of it like that. A quantum, a quantum is the minimum quantity of energy that can either be lost or gained by an atom. A quantum is the minimum. Minimum means the least amount of energy that could be lost or gained by an atom. Now, they want you to think of an analogy of a brick wall. If you have a brick wall in front of you, and that is your object, right? That's your hot object. And that wall can only undergo a change in height by units of one or more brick, and not by any possible height. So if you have a tall brick wall and that is your hot object, and the change in height is the energy that's either being lost or gained, well, you're only going to be losing or gaining or changing that height by removing bricks, right? And as you're removing these bricks, that is that quantum of energy that is being lost or gained by that atom or that object. Now, Planck showed that the amount of radiant energy, so there's a connection. There is a connection about how much energy is absorbed or released by an object, is connected to the frequency of that radiation. Okay, so if you have this light that you have an object and it's showing a particular color, you can measure the frequency of that color and calculate using Planck's constant to calculate energy. Okay. And anytime they're talking about emitting or absorbing. Okay. So let's talk about emitting. Emitting means to release, and to release, right? Emitting means you're giving off. Anytime you give off energy, and in the case we're talking about is atoms, you're going to be going back to that original energy level. Now, anytime that an atom absorbs energy, it gets hit by energy, that's when you're going to have electrons jumping or making those quantum leaps into higher energy levels. Okay. So anytime an atom hits, electrons jump up. Anytime energy is being released, yeah, once you've released that energy that hit you, you're going to come back and make another leap, but the leap will be back into your original energy level or your original orbital. Okay, so here you have a agree or disagree statement. Do you agree with the statement or do you disagree? A quantum is the maximum quantity of energy that can either be lost or gained by an atom. What do you think, guys? Maximum quantity of energy that can be lost or gained by an atom. Do you agree or do you disagree with this statement? What do you think, guys? Is that true? Quantum is the maximum amount of energy that can be lost or gained by an atom. So anytime you heat an object, a quantum, right? Those bursts of energy, is that the maximum amount of energy that can be lost or gained? True. Do you agree or do you disagree with this statement? What do you remember from the last slide? Did we talk about quantums being the maximum quantity of energy, or what? What do you think, guys? Agree or disagree? Pick an answer, please. Pick an answer. Irvin, Alexia, pick an answer. Do you agree or disagree with this statement? Hello? Can you hear me? Is anybody out there? Okay, one person has voted agree or disagree. I need more than one response. Mario, agree or disagree? Did you vote? America, agree or disagree with this statement? Melissa, what about you, Melissa? Jose, Francisca, what do you guys think? And you can put agree or disagree in the chat. Mario says he disagrees, okay? Anybody else? All right, Yalexia, agree or disagree? Put it in the chat. Irvin, agree or disagree? Put it in the chat right now. Efrain, agree or disagree? Put it in the chat right now. Francisca, Jose, Melissa, America, Arlette, agree or disagree in the chat right now, please. I want to see it. I want to make sure that you're listening. Come on, guys. If you're not listening, that means I'm going to just take longer and you're not going to have a chance to leave early. All right. Irvin says he's agreeing. Anybody else? Come on. Efrain, Francisca, Jose, Melissa. I'm talking to you right now. Melissa, Francisca, Efrain. Agree or disagree? Post it in the chat. I'm watching. America says agree or Let says agree. Finally, I'm getting some feedback. 3 people have said that they agree. 4 people in the chat say they agree. Mario's the only one that disagrees. And if we go back to the reading, it says here, a quantum is the minimum quantity of energy. It's the lowest amount of energy, guys. It's not the maximum amount. It's the minimum. It's the least amount of energy. Maximum means todo el energy. It's not. It's doing it in small amounts. It should have been minimum, and you should have disagreed. Very good, Mario. Very good, Mario. The answer was disagree. All right. Now, read what it says at the top. Energy is equal to Planck's constant times frequency. Energy is equal to Planck's constant times frequency. Listen to that, guys. Listen to that. In this equation, E is equal to H times V. E is energy in joules of a quantum of radiation. V is the frequency of the radiation. And H is a fundamental constant called Planck's constant. The value of Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. Now, the energy of any system must either increase or decrease excuse me, in units of H times V. All right, so here we have a small energy change results in the emission or absorption of low frequency radiation, while large energy change results in the emission or absorption of high frequency. And that makes sense. And what they're trying to say is, what do you remember? How do I get low frequency? Do I get low frequency when I have long or short waves? What do you remember about yesterday? Is low frequency long waves or short waves? What do you remember about yesterday? Low frequency, guys. What do you remember? If I have low frequency, that means frequency is going down. Do I have long waves or short waves? What do you remember about yesterday, guys? Were they both pointing up? Were they both pointing down? Or opposite? What do you remember about yesterday? If I have low frequency, Do I have long waves or short waves? Melissa, what do you remember? Low frequency. Long waves or short waves, ma'am? Melissa, I'm talking to you. Melissa. Low frequency, long or short waves? Okay, anybody else? Low frequency, no, it's always long waves. Okay, so if you have long waves, you're talking about the spectrum where you have radio and micro. Okay, those are the least harmful forms of electromagnetic radiation. So you're going to have small changes in energy. Small changes mean that it's not very harmful. Now, if you have high frequency, well, that means you have short waves, small waves. You're talking about gamma and X-ray. That will always give you large, big numbers and big changes in energy. That is the type of electromagnetic radiation that is harmful to people. So you can understand what they're saying about this statement that anytime you have low frequency, you're going to have low energy. Yeah, that makes sense. If I have high frequency, you're going to have high energy. Yes, because high frequency comes from short waves. You're talking about X rays and gamma rays. You know that that's dangerous energy. Low frequency is long waves. That is radio and micro. That's not that dangerous. Okay. Okay. Now, here, there's a question. And I'm going to put the answers that are in the pair deck on the Google chat. A is wavelength. B is Planck's constant. C is frequency. Which variable is not used in the calculation of energy? Which variable is not used to calculate energy? A, B, or C, guys. It's all the answers are in the chat. What do you think is the one that we don't use for energy? Which one is not used to calculate energy? And we just talked about those units we just talked about those variables in the last slide. Excuse me, guys. Sorry. America says A. Anybody else want to vote? America says A. What about everybody else? Alexia, Mario, Jose, Kevin, what do you think? Which one did we not talk about in the last slide? Which one wasn't part of that formula? Which was not part of the formula? Alexia says B. Anybody else? Mario, what do you think? Irvin, Efrain, what do you think? I saw George Flores come in for a second, right? That was in my imagination. Arlette is here. George Flores finally showed up for like a minute and then he left. All right, now let's go back to the last slide. What does it say at the top, guys? Energy is equal to Planck's constant times frequency. Very good, America. You were correct. The answer was A. A is not part of the formula to solve for energy. Okay, nobody gave me responses on Pear Deck. All right, so come back to the Google Meet because I'm going to go to Jamboard, guys, and Jamboard is not on Pear Deck. All right, so here you have a sample problem. The sample problem says, what is the energy of a photon of green light with frequency of 5.75 times 10 to the 14 hertz? Okay, so let's talk about hertz. Okay, hertz, Hz, is equal to 1 over S, which means seconds. Okay, if you look at the units for Planck's constant, you have J times S. So my units will easily cancel. Oh, I totally missed it. We'll cancel that seconds that we're talking about, and we're going to be left in joules, which is what we need for energy. Okay, so I know frequency. We know the formula is energy is equal to Planck's constant times the frequency. All right, so let's plug in our numbers. 6.626 e to the negative 34. Oh, that is not a 4. That is a J or a Y. 34 joules times seconds. And that's going to get multiplied by 5.75 e to the 14th 1 over S. Okay. All I need to do, first off, I'm going to cancel my units for seconds. And I can calculate now my answer in joules. So I'm going to get my calculator. All right. I'm going to turn it to the side. And you're going to see that double E right here. That's the E that I'm talking about that you're going to need. So you're going to put 6.626 E to the 34 negative. Okay, that's Planck's constant. And I'm going to multiply by 5.75 e to the 14th. 14th. And this is my answer, guys. 3.81 times 10 to the 19th power. 3.81 times 10, right? Because that e means times 10 to the negative 19 power. There it is. There it is. All right, if I go back to the presentation, and you don't have to go back because there's no more questions. You have here the same thing that we just did, and we came up with the same answer, 3.81 times 10 to the 19 joules. While the resulting energy may seem very small, right? That's a very small amount of energy. This is only for one photon of light. Anytime you have visible quantities of light, they will consist of huge quantities, hundreds of photons, maybe thousands, a lot. There's always a lot of photons in that energy. Okay. Recall, they talk about hertz and how it cancels out. And we already proved that. So very, very good. All right. We got a video. I'm probably going to do a lot of the explaining. I'll let him do a little bit of explaining, but I like my version better.
E equals hv. Now, E equals hv describes the energy found in a photon. And to get this energy, we need to use Planck's constant, which represents h, to multiply it by the frequency, which represents v. Now, there's a lot to this formula here. We cannot just use this formula. If the question asks us to find the energy, we will also need...
So in order to answer the question that he's going to be doing, you're going to need the formula from yesterday, which is the speed of light is equal to wavelength times frequency. And the formula from today, energy is equal to Planck's constant times frequency. Okay, so look at the question that he asked. Watch. Where is it? Right here. It says yellow light is emitted by sodium lamps in street lights. Hey, Gabby. In street lights has wavelengths of 589 nanometers. That's wavelength. That's not frequency. I cannot calculate energy without frequency, so I need the speed of light formula. So check out what he does. He first off changes his nanometers to meters. So this is a quick conversion. And now that he has meters, he can use the speed of light and divide by his wavelength. So 3 times 10 to the 8th divided by 5.89 times 10 to the negative 7. Once I divide those two numbers, I'm going to get my frequency, 5.09 times 10 to the 14 hertz. Now that I have frequency, I can use the formula for energy, which is right here. Energy is equal to Planck's constant times frequency, and calculate how much energy each photon will release. Okay? And all you got to do is you multiply 6.26 to the negative times 10 to the negative 34 multiplied by 5.09 times 10 to the 10 times 10 to the 14th power, and you get, look at that answer. That answer is really close to the one that we got. We ended up getting 3.81, but that was for green light times 10 to the 19. And if you look on the spectrum, you can see that energy is increasing the further right you go. And look at those colors. They're right next to each other. So you can understand why our answer for green was very, very close to his answer for yellow. 3.37 times 10 to the negative 19 joules. Okay? All right. So let's summarize today's topic. A quantum is the minimum quantity of energy that can either be lost or gained by an atom. The value of Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. Your review questions. These are the ones that we're going to answer right now. Number 1, what did classical physics predict about hot objects? Number 2, what did Planck find? And number 3, what is a quantum? All right, so those are the questions